Hello, so I would like to talk about this most recent archive of mine. So we would like to describe a shape like here, up to rotation. Yeah. So the basic approach is just using the ellipsoid. So we can do it by approximating the shape with covariance matrix. Then its eigenvalues, eigenvectors define ellipsoid like here. We could compare by just testing if the eigenvalues are the same. If so, then they differ only by rotation. However, this provides only a very brief description like here. So here we have some digits, minus digits, and here is its description as approximation as ellipsoid. So we'd like to extend it to higher order polynomial. So maybe let me switch to graphics. Yeah, so we are here. We would like to have rotation-invariant shape descriptors, especially for molecules, for chemoinformatics, that you have molecules, but it doesn't matter how it rotated. We'd like to use methods using these invariants, or maybe shape similarity metric, that we have two shapes, and we'd like to test if they differ only by rotation, but without testing of the rotation. Yes, we just have invariants, and just test the difference of the vectors of invariants. Yeah, so to avoid the rotation optimization. So we can extend it to this covariance matrix defining this ellipsoid to, let's say, this order 3 tensors, higher moments. But we could also do it in a decodable way, that we can know what given what given description means, like Gaussian times polynomial. Yeah, so here is there's Gaussian times constant times the order 1 polynomial, order 2, and we can see that for order like 5 we can recognize the minus digits. So this way we get a description of a shape as polynomial of chosen degree. And now we'd like to build invariants, rotation invariants from them. And we can do it analogously as for this standard similarity test. Yes, that we have the matrix, like covariance matrix, and we test if all its power are equal for two matrices. So this basic test can be represented as a cycle of given length, like M here, and each vertex corresponds to our matrix, each edge corresponds to summation over indexes. So if we rotate it, multiply by some orthogonal matrix, we rotate by it from the one side, by transport from the second, so it vanishes. So it is invariant to rotations. Yeah, so these are well known. And now we would like to take to tensors, so not just degree 2, but degree 3, 4, and so on. So we can do it the same way, but now using graphs of higher order. Like here was only order 2 for matrices, here for order 3, for tensor order 3. So we could build some graphs and then sum over indexes like here. So we have ABC, the three edges, and the three index tensor and squared. Here we have summation over A, yeah, so PAAB, so this is this part, times PBCC. So it is easy to check that all of them do not change if we apply the same rotation to all coordinates. So they form invariant. So with this way we get necessary conditions. So if two shapes are different only by rotation, then all the invariants have to be equal. Yeah, so this way we can get this kind of shape similarity metric, build such vector, and just compare the vectors, or use it as features of a molecule for some machine learning tasks. The difficult part, yes, I think is very interesting, is the sufficient condition. That could we find some complete set of such graphs, such that agreement for all of them allows to imply that the two tensors are differ by just rotation. So for matrices, we know that if you take all the powers of from 1 to the dimension, then we are certain that they provide sufficient condition. But for graphs, it's much more complicated. So I'm trying to prove it and to find a sufficient condition which would have many applications. So thank you for attention.